There is iron at the bottom of the Pacific Ocean that came from an exploding star, not from Earth's formation, not from a meteorite, from a star that died close enough to this solar system to rain its debris across our entire planet roughly 2.5 million years ago. That star was part of a structure above and below the solar system that most people have never heard of, and it is only the third layer in. We are going to work outward tonight, layer by layer, and what sits above and below us is stranger and larger than anything the textbook ever suggested. If that sounds like your kind of evening, subscribe and get comfortable. This one goes all the way to the edge of everything. Let's get into it. Part 1. The slice, not the system. There is an image you have seen so many times that you probably stopped questioning it before you were 12 years old. The sun sits in the center, slightly too large, glowing with that familiar yellow-orange warmth that no photograph of it actually shows. Mercury is closest, then Venus, then Earth with its single moon, then Mars, then the gas giant stretching outward in a neat procession, and finally, somewhere past the small, demoted world that used to be the 9th planet, a dotted line or a vague blur, suggests that the solar system ends. The whole thing fits on a single page. It is orderly, it is readable. It makes sense at a glance, which is precisely why it is one of the most misleading images in the history of science education. That image is not the solar system. That image is a cross-section of the solar system, a single slice cut through the middle, like taking a bread knife to a sphere and then sketching only the cut face and calling it the whole loaf. The actual structure extends in every direction, up, down, sideways, diagonally, at every angle you could name and several you could not easily visualize. It wraps around itself in layers that do not fit on any page without compressing them to the point of uselessness. And the distances involved are not the kind that a human brain handles gracefully. Here is a number that tends to reset people's intuitions. The edge of the solar system, the actual gravitational boundary where the sun's influence fades into something that is no longer meaningfully the sun's domain, sits at roughly 2 light years from where you are, standing right now. 2 light years. Light moves at approximately 299,792,458 meters per second. It covers the distance from Earth to the Moon in about 1.3 seconds. And it takes 2 years of traveling at that speed to reach the outer boundary of the structure we casually call the solar system. Put it another way. Neptune, the outermost recognized planet, orbits at around 30 astronomical units from the Sunday. 1 astronomical unit is the average distance from the Earth to the Sun, approximately 149,600,000 kilometers. So Neptune sits roughly 4.5 billion kilometers out. That sounds enormous, and by human standards, it is. But the gravitational reach of the solar system extends to approximately 100,000 astronomical units. Neptune, the planet you probably think of as the outer edge of the neighborhood, sits at just 0.03% of the actual boundary. It is not the edge. It is not even close to the edge. It is barely past the front door. So what is out there? What exists between Neptune and that real gravitational boundary? What hides above and below the flat plane of the planets, in the directions that the textbook image never shows you? What fills the space that the cross-section quietly erases? These are not rhetorical questions designed to manufacture suspense. They are questions that professional astronomers are actively working to answer, in some cases with missions currently in flight, in other cases with mathematical models that are still debated, and in a few cases with evidence that is genuinely strange enough to suggest that the solar system has a layer we cannot yet explain. The system has a structure, not the flat plate structure, a sphere, or more accurately, a set of nested spheres and layers, each one governed by a different dominant force, each one shading into the next without a clean boundary, each one revealing something about the nature of the universe that the flat plate image completely obscures. There is a bubble of charged solar wind that surrounds us on all sides. There is a warm interstellar cloud that the sun is currently drifting through and will exit within roughly 2,000 years. There is a cavity in the galaxy roughly 1,000 light-years across, carved by ancient stellar explosions whose debris has been found at the bottom of the Pacific Ocean. There is a spherical shell of trillions of icy bodies, so distant and so faint that no telescope has directly imaged a single one of them. Yet we know they exist because their influence occasionally drops through the inner system in the form of long-period comets. And threading through all of it, passing through the walls of every layer, and ultimately through your body right now, is a substance so invisible and so strange that science has spent decades confirming it exists without once identifying what it is. Most of what defines the solar system cannot be seen. That is not a limitation of current technology that will be solved in the next decade. It is a statement about the nature of the structures themselves, sparse, diffuse, distributed across volumes so large that even if you filled them with material, the average density would still be less than the best vacuum a laboratory can produce on Earth. When you look up on a clear night and see what appears to be empty blackness between the stars, you are not seeing nothing. You are looking through layers of structure that are effectively transparent to visible light, but are doing real, measurable work on the solar system and everything inside it. The solar system is full of structure we cannot yet see, and understanding what that structure is and what it does is one of the central challenges of modern astrophysics. The flat plate image gets one thing right: the planets are mostly confined to a disk. But understanding why requires understanding something about how the solar system formed, and that understanding immediately reveals why everything beyond the planets does not share that disk shape. When the cloud of gas and dust that became the solar system began to collapse under its own gravity about 4.6 billion years ago, it was not perfectly still. It had a small net rotation, the kind that builds up from the accumulated nudges of nearby stars, galactic tidal forces, and the chaotic turbulence of interstellar space. As the cloud collapsed, conservation of angular momentum caused it to spin faster and flatten, just the way a ball of pizza dough flattens as it spins. The material that formed the planets was constrained to that spinning disk, so the planets formed in the disk, and they orbit in the disk, and they will probably remain in the disk for as long as the solar system exists. But the farther you get from the center, the weaker that organizing disk force becomes. By the time you are out at the distances where the Oort cloud exists, the original angular momentum of the forming disk has been completely overwhelmed by other forces passing stars, the gravitational tide of the galaxy itself, close encounters with other large masses. The result is that the outer solar system is not a disk at all, it is a sphere. The orderly plane of the planets gives way, somewhere beyond Neptune, to a three-dimensional shell that wraps in every direction and contains an amount of material that dwarfs everything in the inner solar system combined. So, when you ask what hides above and below the solar system, you are really asking what occupies the volume that the flat plate image simply does not draw. And the answer begins with the first invisible structure. We are already inside a structure so large that the entire distance from the Sun to Neptune fits comfortably within it, and so dynamic that its shape is being actively mapped by a spacecraft launched in 2025. But before we get there, consider this. If the flat plate image is wrong, and the real structure is spherical and layered and mostly invisible, what else about the solar system might you have been looking at cross-section all along? Part 2. Above and below isn't empty. The reason most people never think about what sits above and below the ecliptic plane is not ignorance. It is an entirely reasonable response to how astronomy is usually taught. The planets are in the plane. The asteroids are mostly in the plane. The Kuiper Belt, the collection of icy bodies just beyond Neptune that includes Pluto, is roughly in the plane. Everything that appears in the pictures and the diagrams and the animations is in the plane. So the plane seems like the whole story, and the space above and below it seems like a quiet, uneventful void that you would traverse briefly if you were flying a spacecraft from the inner solar system outward before the real geography begins again somewhere else. That assumption is wrong in almost every way it could be wrong. The space above and below the ecliptic is not empty, it is not uneventful. And the reason it does not show up in the diagrams is not because nothing is there, it is because everything there is invisible to the kinds of telescopes that produce the pictures most people associate with astronomy. A telescope that captures visible light, the kind of electromagnetic radiation that your eyes evolved to detect, is effectively useless for mapping the structures that dominate the volume above and below the planetary plane. Those structures are either too diffuse, too cold, too far, or composed of matter that does not emit visible light at all. They are detected through other means: ultraviolet observations, X-ray astronomy, energetic particle detectors, magnetic field measurements, isotopic analysis of rocks and ocean sediments, and the picture they assemble is strange and compelling in ways that the flat plate image never prepares you for. Start with the question of why the planets are in a disk in the first place, and think carefully about what the answer implies for everything beyond them. The disk formed because angular momentum, the rotational inertia of the original collapsing cloud, forced material into a preferred plane. This is not a mysterious force. It is the same physics that makes spinning tops precess, that causes gyroscopes to resist tilting, that flattens rotating galaxies into their characteristic shape. Material, distributed across all angles of a rotating system, gradually migrates toward the equatorial plane as it loses energy through collisions while conserving angular momentum. The result is a disk, and the planets formed in that disk because that is where the material was concentrated. But here is the crucial implication. The disk-forming mechanism only operates efficiently in regions where material is dense enough for frequent collisions. The inner solar system, where the planets are, was dense enough. The outer solar system, where the Oort cloud sits, was not. By the time you reach the distances at which the Oort cloud exists, the original disk geometry has been completely randomized by billions of years of gravitational perturbations from passing stars, the galactic tide, and encounters with giant molecular clouds. The result is a region that is statistically isotropic, meaning it looks approximately the same in every direction, not a disk, a sphere. This geometric transition from disk to sphere, from ordered rotational structure to randomized three-dimensional shell, is one of the most important and least discussed features of the solar system. It means that the system transitions from something that can be mapped on a flat page to something that cannot. It means that the volume above and below the ecliptic is not empty space waiting to be crossed. It is part of the same gravitational system, populated by the same kinds of objects that exist in the plane, but distributed across all angles rather than concentrated in one. There are comets above the ecliptic. There are icy bodies below it. There is material in every direction that was part of the original solar nebula and has been slowly migrating outward and randomizing for 4.5 billion years. And then there is the material that does not belong to the solar system at all, the interstellar medium, the diffuse mix of gas, plasma, dust, and magnetic field that fills the space between stars. This material is not empty. It has a temperature, usually measured in thousands of degrees for the ionized components and in tens of degrees above absolute zero for the cold, dense molecular cloud regions. It has a density, though that density is almost inconceivably low by any terrestrial standard, typically somewhere between 1/10 and 10 atoms per cubic centimeter, compared to the roughly 2.7 times 10 to the 19th molecules per cubic centimeter in the air you are breathing right now. It has a magnetic field, tangled and variable, which interacts with charged particles and shapes the flow of material in ways that are still not fully understood. The point is that when you fly above the ecliptic plane, you do not fly into nothing. You fly into a medium that has structure, that has temperature, that has magnetic topology, and that is actively pressing against the solar system from every direction. The solar system does not sit in a vacuum. It sits in a moving, structured, magnetized fluid, and the interaction between that fluid and the solar wind is what creates the first invisible layer of the system, the one that we are inside right now and have barely begun to map. Every direction above and below the plane is filled with that interaction. None of it is visible to the naked eye. All of it is doing real physics. And understanding it turns out to be more urgent than most people realize, because we are not passive observers of that physics, we are inside it. Part 3. The first boundary we didn't know we were inside. The sun is not quiet. It has been shedding material continuously for 4.5 billion years, pushing out a stream of charged particles, mostly electrons and protons, in every direction at speeds that typically range from 300 to 700 kilometers per second. This is the solar wind, and by the time you are reading or listening to this, it has already crossed the distance from the Sun to Earth in roughly 4 days and swept outward past every planet in the system. It does not stop at Neptune. It does not stop at Pluto. It keeps going, pushing against the interstellar medium, until the outward pressure of the solar wind finally equals the inward pressure of everything outside it. The region defined by the solar wind's reach, the volume of space that the sun is effectively inflating with its own continuous exhalation, is called the heliosphere. You are inside it right now. The entirety of human history, every spacecraft ever launched, every telescope ever pointed at the sky, every signal ever sent or received has occurred inside the heliosphere. It is the first innermost layer of the structure that sits above and below and around the familiar planetary plane, and until the 1980s and 90s, its precise shape and behavior were almost entirely theoretical. We could infer its existence from the behavior of the solar wind, we could estimate its extent from pressure balance equations, but we could not visit its boundary, and we had no instruments at the edge of it to send back data from the outside. Then Voyager happened. Voyager 1 and Voyager 2 were launched in 1977, and after 4 decades of travelling outward at roughly 17 and 15 kilometers per second respectively, they crossed what is called the termination shock, the first major boundary within the heliosphere, where the solar wind slows from supersonic to subsonic speeds, and eventually, in 2004 and 2007, they entered the heliosheath, the turbulent outer region of the heliosphere where the solar wind becomes chaotic and compressed. Voyager 1 crossed the heliopause, the actual outer boundary where solar wind pressure and interstellar pressure balance in 2012 at a distance of roughly 121 astronomical units from the Sunday. Voyager 2 crossed it in 2018 at roughly 119 astronomical units, on the opposite side of the solar system. Those 2 crossings immediately revealed something important. The boundary is not spherical. Voyager 1 and Voyager 2 took different paths and crossed the heliopause at different distances, which means the heliosphere is asymmetric thicker in some directions than others. This was expected to some degree, because the solar system is moving through the interstellar medium at roughly 26 kilometers per second, creating something like a bow shock in front and a long, trailing region behind. Think of it the way you might think of the wake behind a boat moving through water. The pressure is higher on the leading edge and lower on the trailing edge, and the shape of the disturbance reflects that asymmetry. But the exact shape of the heliosphere turned out to be stranger and more debated than the simple bow shock model predicted. This is where things get genuinely puzzling in a way that researchers are still arguing about. In 2009, the IBEX mission, the Interstellar Boundary Explorer, began mapping the heliosphere from inside by detecting a specific type of particle called energetic neutral atoms, which form at the heliopause when charged particles exchange electrons with neutral interstellar atoms and go electrically neutral, allowing them to travel in straight lines back to the inner solar system where IBEX can detect them. The resulting map was expected to show a smooth, roughly symmetric glow of these particles coming from the direction of the heliopause. Instead, it showed a bright, narrow ribbon of emission that wrapped around the sky in a great arc, far more intense and far more structured than any model had predicted. The IBEX ribbon, as it came to be called, is still not fully explained. It is too narrow and too ordered to be accounted for by simple pressure balance models. Several competing hypotheses have been advanced. One suggests it marks regions where the interstellar magnetic field happens to be oriented tangent to the heliopause, causing particles to be efficiently reflected back inward. Another suggests it is produced by secondary neutral atoms formed outside the heliosphere that re-enter and become detectable. A third invokes turbulent processes in the heliosheath that concentrate particles along specific magnetic field lines. None of these explanations is universally accepted. The ribbon is real, it is measured, it is reproducible, and its physical origin remains an open question. This matters for the central story we are telling, because the IBEX ribbon is not a cosmetic detail. It is evidence that the shape and behavior of the heliosphere, the first layer above and below us in every direction, is governed by physics we do not fully understand. We are inside a magnetic bubble whose geometry we cannot yet determine, whose boundaries are irregular and responsive to the interstellar environment, and whose detailed structure is currently being mapped by a follow-up mission called IMAP, the Interstellar Mapping and Acceleration Probe launched in 2025. The heliosphere is not a known quantity. It is an active frontier of investigation. And the reason it matters goes beyond scientific curiosity, because this bubble is the first thing standing between the inner solar system and the interstellar environment that surrounds it. Part 4. The edge that isn't an edge. People use the word boundary in a way that implies something solid, something you could touch or point to, something that divides one region cleanly from another the way a wall divides two rooms. The heliopause, the nominal outer boundary of the heliosphere, is not like that. It is a region of pressure equilibrium, not of physical surface. There is no wall, there is no line. There is a zone, probably thousands of astronomical units, thick in some directions and thinner in others, where the properties of the solar wind gradually shade into the properties of the interstellar medium, and where trying to say exactly which side of the boundary you are on becomes a matter of definition rather than measurement. Voyager 1's crossing of the heliopause was not a sudden event detected in a single data file on a single day. It was inferred after the fact from a combination of measurements, a drop in solar wind particle counts, a rise in interstellar particle counts, a change in the magnetic field direction that converged to suggest that the probe had moved from one regime to another. The interstellar medium outside is denser, hotter in terms of particle energy, and differently magnetized than the solar wind inside. But the transition between them takes time, takes distance, and is not clean. Before the heliopause, the solar wind passes through a region called the heliosheath. This is the zone between the termination shock, where the solar wind first slows down, and the heliopause, where it finally stops pushing outward against the interstellar pressure. The heliosheath is turbulent. The solar wind in this region has been compressed, decelerated, heated, and stirred by its interaction with the oncoming interstellar medium. Voyager 1 spent roughly 7 years in the heliosheath before crossing the heliopause. 7 years at 17 kilometers per second, traveling through a zone of increasing chaos between the bubble's edge and its environment. What Voyager 1 found when it crossed the heliopause also surprised researchers. The magnetic field did not reorient as much as predicted. The cosmic ray environment changed, but in ways that suggested the heliopause is not a hermetic seal. Charged particles from outside were already leaking in before the crossing, and solar particles were still detectable, faintly, after it. The heliopause leaks. It is permeable to high-energy particles in a way that a true wall would not be. Think of it like a coastline, rather than a cliff. There is an edge in the sense that the ocean and the land are clearly different things, but the exact line between them moves with every wave and tide, and the transition zone of wet, sand, and spray is neither fully one nor fully the other. This permeability is not a trivial detail. It means that the interstellar environment does not simply press against the heliosphere from outside. It penetrates it continuously in the form of high-energy particles called cosmic rays. These are charged particles, mostly protons and atomic nuclei, accelerated to enormous velocities by distant astrophysical events. Supernova shockwaves, the jets of active galactic nuclei, magnetar flares. They travel across interstellar space at close to the speed of light, and when they reach the heliosphere, the solar wind and the magnetic field deflect some of them, but not all. A significant flux of cosmic rays reaches the inner solar system, and some of them reach Earth. The Sun's own magnetic activity modulates this flux during solar maximum. When the solar wind is stronger, fewer cosmic rays get through, and during solar minimum, more do. The heliosphere is not an impenetrable shield. It is a partial, variable screen, and what it screens against is coming from directions above and below the ecliptic plane just as much as from any other direction. The fact that this boundary is not an edge but a gradient, that it leaks, that it responds to its environment, these properties are not incidental features of the heliosphere. They are fundamental to understanding what the solar system actually is. It is not a closed system. It is not isolated. It is permeable and responsive and embedded in something larger, and the way material crosses the boundary in both directions is part of the physics that connects everything inside to everything outside. The solar system ends not with a wall, but with a negotiation, a continuous balancing act between the sun's outward push and the galaxy's inward press. And right now, that negotiation is happening in every direction, above and below you, at distances of roughly 100 astronomical units, being monitored by 2 aging spacecraft traveling on battery power through a frontier that looks nothing like the textbook said it would. Part 5. The first crack in isolation. Here is something worth pausing on. The heliosphere is often described as a protective bubble, a kind of planetary defense system that shields the inner solar system from the radiation environment of interstellar space. That framing is not wrong exactly, but it is incomplete in a way that matters. It implies that the solar system is isolated inside its bubble, looking out at a dangerous universe through a sturdy window. The reality is that the window has cracks, or rather, it was never a window to begin with. It is more like a net, and what gets through the net is not trivial. Cosmic rays are the most direct example of the outside environment reaching inside. These particles, stripped atomic nuclei and lone protons accelerated by supernova shockwaves and other violent astrophysical events, hit the heliosphere from all directions, including from directly above and below the ecliptic plane. The heliosphere deflects many of them, but the ones with the highest energies punch straight through. They reach Earth. They interact with the upper atmosphere, triggering cascades of secondary particles that rain down to the surface. Some of them penetrate to ground level. Some of them pass through your body right now, every single day, leaving a trail of ionization along their path through your tissues that your cellular repair mechanisms clean up quietly and efficiently in the vast majority of cases. The flux of cosmic rays reaching Earth is not constant. It tracks the solar cycle. When the Sun is active at solar maximum, the stronger solar wind creates a more robust heliosphere that deflects more cosmic rays, and the count rate at Earth drops. When the Sun is quiet at solar minimum, the heliosphere weakens slightly, and more cosmic rays get through. This 11-year modulation is measurable in cosmic ray detectors around the world. It has biological implications that are still being studied. Elevated cosmic ray flux has been linked to slightly increased radiation exposure for high-altitude air travelers and astronauts, and some researchers have proposed connections to cloud formation through a mechanism involving cosmic ray ionization of the atmosphere, though that link remains contested. The key point for the story we are building is this. The heliosphere is the first innermost layer of the structure above and below the solar system. And even this innermost layer is not sealed. The outside gets in. The interstellar environment is already influencing conditions in the inner solar system through the continuous leak of cosmic rays, through the modulation of particle fluxes that depends on the shape and strength of the heliospheric magnetic field, through the very geometry of a boundary that responds to changes in the interstellar medium it is embedded in. The solar system is permeable from the first layer outward, and the farther out you go past the heliopause, into the structures that surround the heliosphere, the more that permeability becomes a central feature of the story. Because if the innermost layer already leaks, what does that imply about all the layers beyond it? Part 6. The Realization. Let's take stock of where we are. You have a star, the Sun, that has been continuously blowing a bubble of charged particles outward into interstellar space for 4.5 billion years. That bubble surrounds the entire planetary system, not just in the plane of the planets, but in every direction, above and below, wrapping the whole structure in a sphere of solar influence that extends to roughly 100 astronomical units. Inside that bubble, the solar wind flows outward, carrying the Sun's magnetic field with it, creating the structured, magnetized environment that the planets, including Earth, have evolved within. Outside that bubble, the interstellar medium presses inward, not aggressively, not violently, but continuously, maintaining the equilibrium that defines where the bubble's edge sits. Now here is the thing that tends to shift people's perspective when they sit with it long enough. The shape of that bubble, the heliosphere, is not determined by the Sun alone. The Sun supplies the outward pressure, but the size and shape of the bubble is determined by the balance between that outward pressure and the inward pressure of the interstellar medium. Which means that if the interstellar medium changes, if the density or the temperature or the velocity of the gas outside changes, the heliosphere responds. It grows or it shrinks. It shifts its shape. It adjusts its boundary. The bubble is not a fixed structure. It is a responsive one, and what it is responding to is the environment outside it. And that environment is not uniform. The Sun is moving through the galaxy at roughly 26 kilometers per second relative to the local interstellar medium, which means it is continuously encountering new material. The interstellar medium is not a featureless, uniform gas. It is structured, with regions of different density and temperature and magnetic field strength. As the Sun drifts through this structured medium, the heliosphere encounters different conditions and responds differently. There are periods in the past when the Sun was passing through denser interstellar material, and the heliosphere was almost certainly smaller and more compressed than it is today. There are periods, perhaps future periods, when the Sun may encounter regions dense enough to compress the heliosphere dramatically enough in theoretical models to bring the boundary inside the orbit of the outer planets. We will come back to that thought because its implications are significant. The realization, the one that Act 1 has been building toward, is this. The heliosphere is not the outside of the solar system. It is the inside, of the next layer. It is the innermost shell of a nested structure, and it is already in active conversation with the structure that surrounds it. The solar system is not isolated. It has never been isolated. It is embedded in a cloud, in a cavity, in a galaxy, in a halo of invisible matter, and the layers of that embedding extend outward in every direction, above and below and to every side, in ways that the flat plate textbook image does not begin to suggest. What lies outside the heliosphere is not the end of the solar system's story. It is the context within which the solar system's story takes place. And to understand that context, you have to go outward into the cloud. Part 7. The cloud we didn't notice. You would think that a cloud surrounding the solar system would be hard to miss. You would think that something encompassing the Sun, the heliosphere, and all the space around them for tens of light years in every direction would have been noticed fairly early in the history of astronomical observation. But the local interstellar cloud, the cloud the Sun is currently moving through, is made of material so diffuse that it is effectively transparent to visible light. It does not block the stars behind it. It does not scatter light in a way that the eye can see. It is not a nebula with colourful glowing structures and dark lanes and bright ionized filaments. It is, to the naked eye, nothing. It is, to a properly instrumented spacecraft, and to ultraviolet telescopes in orbit, something quite remarkable. The local interstellar cloud is a region of partially ionized hydrogen and helium gas, with a temperature of roughly 7,000 Kelvin. 7,000 Kelvin sounds hot. It is hotter than the surface of the Sun, which sits at about 5,700 Kelvin. But in this context, temperature is a measure of the average kinetic energy of the particles in the gas, and the gas is so sparse that the total energy contained in any given volume is negligible by terrestrial standards. The density of the cloud is approximately 3/10 of a particle per cubic centimetre. To give that meaning, the air around you right now contains approximately 2.7 times 10 to the 19th molecules per cubic centimetre. The local interstellar cloud, by comparison, is essentially nothing, and yet it is not nothing. It is a structured, magnetized medium with detectable properties that affect the heliosphere we are inside. The cloud extends for roughly 30 light-years in its longest dimension. On the scale of the galaxy, 30 light-years is a short walk to the corner store. The Milky Way is about 100,000 light-years across. The nearest star to the Sun, Proxima Centauri, is about 4.2 light-years away. The cloud is larger than the distance to several nearby stars, but it is still a tiny puff of material in the context of the galaxy's overall structure. The Sun entered this cloud approximately 60,000 years ago, which means that our species, anatomically modern Homo sapiens, having appeared somewhere between 300,000 and 150,000 years ago, depending on which fossils you are dating, has spent its entire existence inside this interstellar cloud without being aware of it. And here is the thing that immediately reconnects to the structure we are building. The Sun will exit this cloud. Not soon by human standards. The estimated exit time is approximately 2,000 years from now, give or take several hundred years depending on the velocity and density models used. But on geological and astronomical timescales, we are very close to the edge of the cloud that the heliosphere has been embedded in for the last 60,000 years. When the Sun exits the cloud, it will move into a different region of the interstellar medium, one with different density, different temperature, different magnetic field geometry. And when that happens, the heliosphere will respond. It will reshape itself to the new equilibrium. The first layer above and below us will change its size and its character, and the conditions inside it will shift accordingly. This is not speculation. This is a consequence of the same pressure balance physics that defines the heliosphere's shape right now. The motion of the solar system through the galaxy is not random wandering. The Sun follows an orbital path around the galactic center, completing one revolution approximately every 230 million years. Along that path, it passes through different regions of interstellar material, dense clouds, sparse cavities, regions of recent star formation, and regions of quiet old stellar population. The heliosphere responds to every transition between these regions. The cloud we are currently in is just the most immediate and most measurable example of a continuous interaction that has been shaping the solar system's environment throughout its history. We are not drifting through a uniform vacuum. We are drifting through a structured medium, and the structure of that medium leaves marks on the heliosphere, on the planets, possibly on the long-term history of life on Earth. The cloud we did not notice turns out to be telling us something important about the nature of the space above and below the solar system, not just in the current era, but across the billions of years of the solar system's history. And the story it tells is one where the solar system is never isolated, never static, and never truly sealed from its surroundings. We are moving through something. And the something we are moving through is about to change. Part 8. The solar system has weather. When astronomers talk about conditions in the interstellar medium affecting the solar system, it can sound abstract, interesting in a theoretical way, but distant from anything that matters. So let's make it concrete. The heliosphere, as we established, is defined by the balance between solar wind pressure pushing out and interstellar medium pressure pushing in. Right now, that balance sits at roughly 100 astronomical units in the direction facing the interstellar wind. If the interstellar medium became denser, if the Sun drifted into a region with 10 times more particles per cubic centimeter, the pressure pushing in from outside would increase. The heliosphere would shrink. The termination shock would move inward. The heliopause would compress. In an extreme scenario, the heliosphere could shrink to a fraction of its current size. How extreme could it get? Theoretical models of heliosphere compression in dense interstellar environments produce results that are genuinely striking. Some models suggest that if the Sun passed through a dense molecular cloud, the kind of cold, dark cloud where stars form, with densities of thousands of particles per cubic centimeter, the heliosphere could compress to somewhere around 1 astronomical unit. That is the distance from the Sun to Earth. In that scenario, the protective bubble that currently extends beyond Neptune would shrink to the point where Earth's orbit sits near the outer boundary. The planet would be, effectively, at the edge of the heliosphere, exposed to significantly elevated levels of interstellar radiation and energetic particles from outside the bubble. We have probably passed through dense interstellar environments at various points in the solar system's history. The galaxy is not uniform. There are regions of it where the interstellar medium is dense enough, and has been for long enough periods, that a passing star system would experience dramatic heliospheric compression. What would that mean for the planets inside? Elevated cosmic ray flux reaching the inner solar system. Changes in atmospheric chemistry on Earth, driven by increased ionization. Possible effects on the ozone layer. Effects on cloud formation and surface temperature. These are not confirmed mechanisms of past extinctions or climate changes. The causal chains are long and uncertain, but they are plausible physical consequences of a real, documented process. The Sun is currently in a relatively benign stretch of interstellar medium, in a hot, low-density cavity that provides comfortable conditions for the heliosphere. But that is the current snapshot. Over the 4.5 billion years of the solar system's history, the Sun has passed through many different interstellar environments, and the heliosphere has responded to each of them. This is what it means to say the solar system has weather, not weather in the terrestrial sense of rain and wind and temperature swings on a daily cycle, but weather in the cosmic sense of changing environmental conditions over timescales of millions to tens of millions of years, driven by the solar system's motion through a structured, varied interstellar medium. Understanding this cosmic weather is directly connected to the central insight of the whole structure above and below us. The heliosphere, the first layer, is not independent of its surroundings. It is continuously shaped by them. And those surroundings, the interstellar cloud and the cavity beyond it, are themselves the product of processes that connect the solar system to the galaxy in ways that go far beyond simple orbital mechanics. The next layer of the structure the cavity the cloud is embedded in is where those connections become dramatic, physical, and, as it turns out, measurable in ocean sediment at the bottom of the Pacific. Part 9. The room around the cloud. Step back further. The local interstellar cloud is embedded in something larger. The cloud is roughly 30 light-years across, but the cloud itself is just a dense pocket of material within a much larger, much hotter, much more diffuse structure called the local bubble. The local bubble is a roughly spherical cavity in the interstellar medium that extends for approximately 1,000 light-years in some directions, containing within it the Sun, dozens of nearby star systems, and a thin, hot plasma at temperatures around 1 million Kelvin, far hotter than the surfaces of any of the stars within it. The local bubble was not always there. Something made it. In fact, several somethings made it, and the story of what made it is one of the more dramatic chapters in the recent history of astrophysics. The current best estimate, based on the kinematics of nearby stars and the distribution of hot gas in the bubble, is that the local bubble was carved out by the explosions of somewhere between 14 and 20 massive stars over the past 10 to 15 million years. These stars, which were probably part of a nearby star-forming region or a young stellar cluster moving through this part of the galaxy, lived fast and died violently. When a star more than about 8 times the mass of the Sun exhausts its nuclear fuel, the core collapses in a fraction of a second, and the resulting explosion, a supernova, releases roughly 10 to the power of 44 joules of energy. To give that number some meaning, that is more energy than the Sun will emit in its entire 10 billion year lifetime, released in a few seconds. A single supernova sends a shockwave expanding through the surrounding interstellar medium at thousands of kilometers per second. As the shockwave expands, it sweeps up gas and dust, compresses it into a dense shell at the leading edge, and leaves behind a hot, diffuse, low-density interior. The shell slows as it sweeps up more material, eventually decelerating to the point where it stalls and disperses into the surrounding medium. But if multiple supernovae occur in the same region over a short period of time as they would in a cluster of massive stars, which tend to explode within a few million years of each other because their lifetimes are all similarly short, the combined shock waves can carve out a much larger cavity than any single explosion could produce. That is what happened to create the local bubble. 14 to 20 supernovae, over a period of roughly 10 to 15 million years, excavated a volume of roughly 1,000 light-years across, sweeping the interstellar gas outward into a surrounding shell and leaving behind the hot, low-density interior that the Sun is currently drifting through. The Sun was not in the region when the supernovae occurred. It arrived at its current position within the bubble more recently. But the bubble it now occupies is the direct product of those ancient stellar deaths. We are living inside a supernova remnant. Not one supernova, but the combined remnant of up to 20 of them, and the hot gas filling that remnant is the material that those stars expelled in their final moments, and the interstellar medium that their shock waves heated and dispersed. This is the room around the cloud. The cloud we are drifting through sits inside a cavity that was blasted open by stellar explosions. The entire neighborhood of the solar system, the few hundred light-years in every direction, above and below the ecliptic and to every side, is this supernova-excavated bubble filled with hot, low-density plasma, surrounded by a compressed shell of denser material at its edges. The structure is not static. New observations suggest the bubble is still expanding slowly, and its boundary is irregular, overlapping with adjacent bubbles created by other supernova clusters in the galaxy. The galaxy, at scales of hundreds of light years, looks not like a smooth medium, but like a foam of overlapping cavities and compressed shells, each one the product of stellar feedback from massive stars that lived and died and reshaped their environment in the process. And the story of how we know this, how we know that the cavity exists, that supernovae created it, that those supernovae were real and recent on astronomical timescales, includes evidence that is not in a telescope or a satellite measurement. It is in the ocean floor, waiting to be scooped up and analyzed. Part 10. The evidence beneath your feet. Here is a fact that tends to make people stop and reread the sentence. Embedded in the crust of the Pacific Ocean floor, at depths of several kilometers below the surface, there is a measurable layer of iron-60. Iron-60 is a radioactive isotope of iron, meaning it has an unstable nucleus that decays over time, emitting radiation and converting into another element. Its half-life is approximately 2.6 million years. This means that any iron-60 that existed when Earth formed 4.5 billion years ago has long since decayed. It is completely gone. The iron-60 in the ocean floor is not primordial. It arrived from somewhere else, after the Earth was already fully formed within the last few million years. The only natural process capable of producing significant quantities of iron-60 is a supernova. In the nuclear furnace of a massive star's core, and in the shockwave of the explosion that destroys that star, conditions exist that allow the fusion of heavy elements, including iron-60. When the star explodes, it ejects this material at high velocity. The ejector expands into the surrounding interstellar medium, some of it in the form of dust grains that can travel across interstellar distances before settling into planetary surfaces and ocean floors. The iron-60 layer in the Pacific crust is, in the most literal sense, stardust material from a dying star that crossed the interstellar void and sank to the bottom of our ocean. The layer has been dated. The iron-60 was deposited approximately 2.5 million years ago, with a possible secondary deposition event around 8 million years ago. 2.5 million years ago places the event in the Pliocene epoch, around the time of the emergence of early Homo, the genus that would eventually produce Homo sapiens. Whether there is any connection between the elevated radiation environment following a nearby supernova and the evolutionary history of the hominid lineage around that period is speculative, but it is a question that researchers have genuinely asked. The same iron-60 signature has been found in lunar samples returned by the Apollo missions, confirming that the source was extraterrestrial and not a product of unusual geochemical processes on Earth. It has also been found in sediment cores from other ocean basins, suggesting a globally distributed deposition event consistent with material arriving from a specific interstellar direction. The supernova that produced this iron-60 was probably within a few hundred light-years of the solar system, close enough for the ejector to travel across the gap within the relevant timescale, but far enough that the explosion itself did not cause catastrophic damage to the inner solar system. What this means, in the context of the structure above and below us, is direct and striking. The evidence of the local bubble's formation, the explosions that carved the cavity we are drifting through, is not just visible in telescope data and hot plasma surveys. It is physically present on Earth. The structures above and below us are not remote astronomical phenomena. They are connected to the planet through material traces, isotopes, deposited by stellar explosions, cosmic rays modulated by the heliosphere's response to its environment, interstellar dust grains that fall continuously into the inner solar system from the medium surrounding us. The layers above and below leave measurable physical imprints on the only world you have ever touched. Part 11. The non-random position problem. There is a detail about the Sun's position within the local bubble that deserves attention because it is, by a strict probabilistic argument, unusual. The Sun is not at the edge of the local bubble. It is not buried in the compressed shell at the boundary. It sits near the geometric center of the cavity, and that turns out to be a statistically interesting place to be. Think about what the local bubble is. It is a region of space that was excavated by supernova explosions from a cluster of massive stars. The supernovae presumably occurred somewhere within or near the current volume of the bubble. The stellar remnants, neutron stars, black holes from those explosions, are somewhere in the galaxy, having moved from their original positions over the millions of years since the explosions. The gas of the bubble has expanded outward, and the Sun, which was not in this region when the explosions occurred, has since drifted into the center of the cavity on its galactic orbit. For the Sun to be near the center of a bubble created by massive stars, those massive stars would have had to be in approximately the same region of the galaxy as the Sun's current position, which means they would have had to be near the Sun's previous positions along its galactic orbit in the 10 to 15 million years during which the bubble was being excavated. Some researchers have proposed that the Sun may have actually formed in the same stellar cluster as the massive stars that created the local bubble, or passed through the cluster region during the relevant period. Stellar motion reconstructions, calculations that run the trajectories of nearby stars backward in time to find where they were millions of years ago, provide some support for the idea that a group of stars currently scattered across several hundred light-years of space were once closely associated. This is not a solved problem. The statistical argument for non-random positioning is real, but contested. The local bubble is large enough, and the galaxy's stellar distribution is structured enough that the Sun being near the center might not be as improbable as it first sounds. But the question of how the Sun came to be in its current position within a supernova excavated cavity, and whether that position is coincidental or causally connected to the history of the surrounding stellar population, is genuinely open. It adds another layer to the already strange picture of the solar system's position in the galaxy. We are not just anywhere. We are in a specific location with a specific history, sitting at what appears to be the interior of an ancient stellar catastrophe, and the physics of our position continues to shape the environment above and below us right now. Part 12. The Shift in Perspective. Here is how the picture has changed since the beginning of this story. We started with the flat plate Sun in the middle, planets on a line, a vague edge somewhere. We replaced it with a sphere of solar influence, the heliosphere, extending in every direction to roughly 100 astronomical units. We then embedded that sphere in a warm, partially ionized cloud, 30 light-years across, that the Sun entered 60,000 years ago and will exit within 2,000 years. And we embedded that cloud inside a cavity 1,000 light-years across, blasted open by the explosions of up to 20 massive stars, filled with million Kelvin plasma and surrounded by compressed shells of denser material. The layers are nested. Each one is larger by a factor of 10 to 100 than the one inside it. Each one is governed by a different dominant physics: solar wind pressure for the heliosphere, thermal and ionization state for the cloud, supernova shock dynamics for the bubble, and each layer is connected to the one inside it and the one outside it through the continuous exchange of material and energy cosmic rays, penetrating inward, solar wind pushing outward, interstellar neutrals diffusing through the heliopause, supernova ejecta settling into ocean floors. The shift in perspective is this: space above and below the solar system is not empty, it is structured. The structure has a history, the history of supernovae, of stellar cluster dynamics, of the Sun's orbit through a varied and non-uniform galaxy. That history is written in the present configuration of the layers, and we can read parts of it from ocean sediments and lunar samples, and the data coming back from two 47-year-old spacecraft on the edge of the heliosphere. The structures above and below us are not decoration. They are the context within which the solar system exists, the environment that shaped its history and continues to influence its present. And we have not yet talked about the largest structure. We have not yet talked about the layer that contains all of these, the heliosphere, the cloud, the bubble, and dwarfs them so completely that the local bubble itself is a tiny feature within it. We have not yet talked about the structure that is held together not by pressure or plasma dynamics but by gravity alone, that contains trillions of objects no telescope has ever directly imaged, and whose outer boundary sits not at 100 astronomical units, or 30 light-years, or 1,000 light-years, but at 2 full light-years from the Sunday. That structure is the Oort cloud, and it is the true boundary of the solar system, and it is full of mysteries that the inner system gives almost no hint of. Part 13. The largest structure you've never seen. Jan Oort was a Dutch astronomer working in the mid-20th century, and in 1950 he published a paper that proposed the existence of a structure that nobody had ever observed, using evidence that was entirely indirect, arguing for a population of objects in a region of space so remote that no instrument of his era or any era since could possibly detect them directly. He called it a cloud of comets surrounding the solar system at enormous distances, and the argument he made has held up for more than 70 years. The Oort cloud is real. It has never been directly seen, and it is probably the largest and most massive component of the solar system you never hear about. The evidence for the Oort cloud comes from long-period comets. These are comets that fall inward through the solar system on orbits, with periods measured not in years or decades, but in thousands or millions of years. When you track the orbital path of a long-period comet backward, when you calculate where it came from, how far out its orbit extends, you find that the aphelion, the farthest point of the orbit, is typically at distances of tens of thousands to hundreds of thousands of astronomical units from the Sunday. These comets are coming from somewhere, and that somewhere is a spherical shell of material at enormous distances from the inner solar system. That is the Oort cloud. The estimated population of the Oort cloud is staggering. Models suggest it contains somewhere between 100 billion and several trillion individual objects, ranging in size from small, icy bodies a few hundred meters across to objects potentially several hundred kilometers in diameter. The total mass is uncertain, but is estimated to be somewhere between 1 and several times the mass of Earth. This material is distributed throughout a volume of space that extends from roughly 2,000 astronomical units, well beyond the Kuiper belt, out to somewhere between 100,000 and 200,000 astronomical units, which puts the outer boundary at 1 to 2 light-years from the Sunday. 1 to 2 light-years. Not from the center of the galaxy, from the Sunday. The Oort cloud fills the space in every direction above, below, to every side, out to a distance that is close to halfway to the nearest star. It is not a disk. It is not confined to the ecliptic plane. It is a sphere, an enormous, tenuous, invisible sphere of icy bodies that defines the true gravitational extent of the solar system. And we have never directly imaged a single one of them. Not one. The Oort cloud is the largest thing in the solar system, and it is entirely a theoretical construct supported by indirect evidence that happens to be compelling enough that essentially no astronomer disputes it. When a long-period comet arrives in the inner solar system, when it falls past Jupiter, grows a tail from solar radiation and solar wind, and blazes across the sky in a display that humans have regarded as omens and portents throughout all of recorded history. It is a visitor from that invisible sphere. It has been sitting out there at a distance of tens of thousands of astronomical units, on an orbit so slowly evolving that one circuit takes millions of years since the early solar system. Something perturbed. It gave it a gravitational nudge that altered its orbit enough to send it falling inward. That something could be a passing star. It could be the galactic tide. It could be a close encounter with a dense molecular cloud. Whatever it was, it reached into the invisible sphere above and below the solar system and pulled one of its objects loose, sending it on a journey inward to the inner solar system that takes thousands of years to complete. The emotional weight of the Oort cloud is strange to articulate, but real once you sit with it. An entire shell of material surrounds the solar system in every direction, at distances that light takes months to cross. It has been there since the solar system formed. It contains more individual objects than there are stars in many galaxies, and we have never seen it. We have only inferred it from the trajectories of the rare objects that fall out of it and travel inward to where our telescopes can find them. The Oort cloud is the solar system's missing bulk, its invisible presence in every direction above and below us, and it is currently hiding secrets that connect to some of the most contested questions in modern planetary science. Part 14. The Geometry Flip. There is a moment in the solar system's architecture, a distance from the Sun, not precisely defined but real, where the geometry of the system changes. Inside that distance, the dominant organizing principle is the disk. The planets, the asteroid belt, the Kuiper belt, all of these are roughly confined to a plane because the angular momentum of the original solar nebula has not yet been fully randomized. Objects in these regions have been orbiting in the same plane for billions of years, disturbed occasionally by planetary resonances and gravitational encounters, but fundamentally constrained by the disk geometry of the system's formation. Outside that distance, the dominant organizing principle is chaos, not chaos in the sense of randomness, but chaos in the mathematical sense of sensitive dependence on small perturbations. Objects in the outer solar system have had their orbital parameters slowly randomized by a combination of three forces: passing stars, whose gravitational influence reaches across several light years on timescales of millions of years; the galactic tide, the large-scale gravitational field of the Milky Way's disk that exerts a systematic torque on orbits in the outer solar system, and encounters with giant molecular clouds; the cold, dense regions of interstellar space that can perturb orbits when the solar system passes through or near them. Over billions of years, these perturbations have taken the originally disk-confined material of the outer solar system and spread it into a sphere. The technical term for this process is isotropization, the transformation of an anisotropic distribution, one concentrated in a particular direction, into an isotropic one, distributed equally in all directions. The inner solar system is anisotropic concentrated in a disk. The Oort cloud is isotropic distributed in a sphere. The transition between these geometries happens somewhere in the region of a few thousand to tens of thousands of astronomical units from the Sunday, and the physical meaning of that transition is that the outer solar system is the recording of the solar system's dynamical history, 4.5 billion years of gravitational nudges from stars and tides and clouds, all of them inscribed in the three-dimensional distribution of icy bodies in the Oort cloud. Think of the Oort cloud as a memory, a frozen record of every gravitational interaction the solar system has experienced since its formation. Each body in the cloud sits on an orbit that reflects the cumulative effect of every perturbing force it has experienced over the age of the solar system. The sphere is not random. It has structure regions of higher and lower density, orbital clustering signatures that reflect the influence of specific past events, but that structure is far too subtle and far too spread across too large a volume to be mapped with current technology. What we can do is use the comets that fall inward from the cloud as samples messengers from the invisible sphere, carrying in their orbits the imprint of whatever last perturbed them, carrying in their composition the chemistry of the early solar system preserved in deep freeze for billions of years. The geometry flip from disk to sphere is not just an architectural curiosity. It represents the point at which the solar system's internal order gives way to external influence. Below that distance, the Sun dominates. Beyond it, the galaxy begins to have a say. And understanding where that transition happens and what the geometry of the Oort cloud tells us about the forces shaping it is directly connected to one of the most compelling open questions in the outer solar system. The question of whether something unknown is hiding out there, shaping orbits in ways that cannot be explained by any force we have already accounted for. Part 15. The edge of the Sun's control. Every massive body in space has what is called a Hill sphere, the region within which its gravity is strong enough to dominate the orbital dynamics of smaller objects against the gravitational competition of other nearby masses. For the Earth, the Hill sphere extends to roughly 1.5 million kilometers, which is why the Moon orbits Earth rather than the Sun at that distance. For the Sun, the Hill sphere extends to roughly 1.5 to 2 light-years, precisely the region occupied by the outer Oort cloud. This coincidence is not a coincidence. The Oort cloud exists at the outer edge of the Sun's gravitational dominance, because that is the furthest distance at which the Sun's gravity can hold onto objects against the competing influence of the rest of the galaxy. Objects inside the Hill sphere are bound to the Sunday. Objects outside it are not. The Oort cloud sits at the transition, its inner regions more securely bound, its outermost reaches in a kind of gravitational borderland where the Sun's pull and the galactic environment's pull are roughly comparable. In this borderland, the galactic tide becomes significant. The galactic tide is not a tide in the terrestrial sense. It is not the gravitational pull of a nearby massive body oscillating with distance. It is the large-scale gravitational field of the Milky Way's disk, which is not perfectly symmetric and exerts a net force on objects in the outer solar system perpendicular to the galactic plane above and below it. This tidal force is strongest for objects whose orbits are inclined at certain angles to the galactic plane, and over time, it systematically modifies orbital parameters in ways that can send objects from the outer Oort cloud falling inward toward the inner solar system. The galactic tide is, in fact, one of the primary mechanisms proposed for delivering long-period comets to the inner solar system. It reaches into the invisible sphere above and below us and gently, continuously shakes it, occasionally knocking loose an icy body that begins the long fall inward. The boundary region of the Oort cloud, the zone where the Sun's gravity and the galaxy's gravity are roughly balanced, is a place of gravitational instability. Objects there are weakly bound, easily perturbed, responsive to forces that would be negligible at smaller distances from the Sunday. A passing star that comes within a light year of the Sun, not an extremely rare event on astronomical timescales, can send shock waves through the outer Oort cloud, perturbing thousands of objects onto new orbits, some of which will eventually fall inward. The galactic tide does its steady work over millions of years. Encounters with molecular clouds can perturb the cloud on an even larger scale. The Oort cloud is not a static archive. It is a dynamically active population being continuously shuffled by external forces. And this brings us to a specific question that the outer solar system has been posing to astronomers for about a decade. Some of the objects beyond Neptune have orbital parameters that cannot be explained by the known forces acting on them. Their perihelia, the closest points of their orbits to the Sun, are too distant to have been pushed there by Neptune's gravity, and their orbital planes show a clustering that is statistically anomalous. Something appears to be shaping their orbits, something that we have not yet found. Part 16. The Orbital Crime Scene. Sedna was discovered in 2003, and it immediately broke the existing models of the outer solar system. It is a small world, probably about 900 kilometers in diameter, and it orbits the Sun on an extremely elongated path. Its perihelion, the closest it ever gets to the Sun, is about 76 astronomical units. Its aphelion, the farthest it goes, is estimated at around 937 astronomical units. Its orbital period is approximately 11,400 years. Here is why Sedna is a problem. The standard mechanism for placing an object in an elongated, distant orbit like Sedna's is a gravitational encounter with a massive planet, specifically Neptune, which is known to scatter small bodies in the Kuiper belt onto new orbits. But Sedna's perihelion of 76 astronomical units is far too distant for Neptune to have influenced it. Neptune sits at 30 astronomical units. To scatter an object to a perihelion of 76 astronomical units, you would need a scattering body at something like that distance. There is nothing known at 76 astronomical units that could have done this. Sedna is not alone. Several other extreme trans-Neptunian objects have been discovered with similarly bizarre orbits, large perihelia, extreme eccentricities, and, critically, a clustering in their orbital parameters. When you plot the orientations of their orbits, they are not distributed randomly around the ecliptic. They tend to cluster in a particular range of angles, which is statistically improbable if their orbits were determined by random scattering or the galactic tide alone. The probability that this clustering is coincidental has been calculated to be somewhere between 1 in a few hundred and 1 in a few thousand, depending on the specific objects included in the analysis and the statistical method used. Something is organizing these orbits. Something with enough mass and at a large enough distance to exert the kind of systematic gravitational influence on a group of objects across a wide range of distances from the Sunday. The clustering is, in essence, an orbital crime scene evidence of a force acting on the outer solar system that the known planetary system cannot account for, and the most natural explanation for a systematic gravitational force shaping the orbits of distant objects is the presence of an unseen massive body somewhere out there in the dark. This connects directly to the central thread. The hidden structure above and below the solar system is not just invisible in the electromagnetic sense, not just undetectable to optical or infrared or radio telescopes. In at least one interpretation of the orbital anomalies, there is a gravitational structure out there, a concentration of mass that we have so far failed to find directly and can only infer from the gravitational fingerprints it leaves on the orbits of smaller bodies. The outer solar system is telling us something is there, we just do not know what. Part 17. The Thing That Might Be There. In 2016, two astronomers at Caltech, Konstantin Batygin and Michael Brown, published a paper proposing what has become known as the Planet 9 hypothesis. Their argument was based on the orbital clustering of extreme trans-Neptunian objects, and it proposed that the simplest explanation for the clustering was the gravitational influence of an undiscovered planet with a mass of 5 to 10 times that of Earth, orbiting the Sun at a distance of somewhere between 400 and 800 astronomical units, on a highly eccentric and inclined orbit with a period of perhaps 10,000 to 20,000 years. Planet 9, if it exists, would be the largest undiscovered object in the solar system since the discovery of Neptune in 1846, which was itself predicted mathematically before it was observed, based on anomalies in the orbit of Uranus. The historical parallel is deliberately invoked by researchers working on Planet 9. Neptune was found because its gravitational influence was detectable in the motions of known planets. Planet 9, in this hypothesis, is revealing itself through the orbital clustering of distant small bodies. The object has not been found. The reason is straightforward. At 400 to 800 astronomical units, even a planet 10 times the mass of Earth would be reflecting very little sunlight. Its brightness would be well below what most current sky surveys are sensitive to. The Vera Rubin Observatory, which began science operations in 2024, is expected to be powerful enough to find Planet 9 within its survey area if the planet exists and happens to be in the region of sky being surveyed. The Subaru telescope has been conducting dedicated searches. So far, nothing has been confirmed. The absence of a detection is not evidence of absence here. It is entirely consistent with the hypothesis, because the object would be faint, slow-moving, and potentially in a part of the sky that has not yet been thoroughly searched. But it is also consistent with alternative explanations that do not require an undiscovered planet, which we will come to shortly. The Planet 9 hypothesis is the most popular of these alternatives, but it is not the only one, and the astronomical community is genuinely divided on whether the orbital clustering it was designed to explain is real, significant, and caused by a single, massive, unseen body. What Planet 9 represents in the structure of this story is the same thing that the ibex ribbon represented for the heliosphere, a specific, quantifiable, instrumentally detected anomaly that points to something we do not yet understand. The heliosphere has an unexplained emission ribbon. The outer solar system has an unexplained orbital cluster. In both cases, the evidence is real. In both cases, the explanation is not settled. In both cases, the anomaly is pointing at structure above and below us that we can detect indirectly but cannot yet directly see. Part 18. Alternative Explanations. The orbital clustering of extreme trans-Neptunian objects has inspired more than one creative hypothesis, and the alternatives to Planet 9 are not frivolous. They deserve mention not because they are all equally likely, but because the fact that multiple different models can explain the same observational data is precisely the kind of scientific situation that should make you cautious about preferring any single explanation too strongly. One alternative is that the clustering is not actually statistically significant. Some researchers have argued that the original statistical analysis was biased by observational selection effects, the fact that trans-Neptunian object surveys are not uniformly sensitive in all parts of the sky, so objects in certain orbital orientations are more likely to be discovered than others. When these selection effects are accounted for more carefully, the clustering becomes less statistically anomalous. This is not a settled argument others have countered, that even corrected analyses retain statistically significant clustering, but it is a legitimate concern about whether the phenomenon is real or an artifact of how the surveys were conducted. A second alternative is a rogue planet captured early in the solar system's history. In the first few 100 million years of the solar system's existence, the giant planets were migrating through the disk, exchanging angular momentum with the smaller bodies around them and with each other. This period of dynamical rearrangement, sometimes called the late heavy bombardment era, may have involved close encounters with passing planetary mass bodies from the forming galaxy. A body with the right mass and the right encounter geometry could have been captured into a wide, eccentric orbit around the Sun, becoming a de facto outer planet without having formed from the same solar nebula. This captured rogue planet hypothesis has different implications from the Planet 9 hypothesis because it predicts a different orbital architecture for the proposed object. A third proposal, perhaps the most exotic, involves a primordial black hole. Black holes formed in the early universe, before any stars existed, from the gravitational collapse of overdense regions in the primordial plasma. These primordial black holes, if they exist and their existence remains theoretical, would have a range of masses and would be distributed throughout the galaxy. A primordial black hole in the mass range of 5 to 10 Earth masses could, in principle, be gravitationally captured by the solar system the same way a rogue planet could. It would be extraordinarily difficult to detect directly because an object of that mass compressed to the size of a golf ball radiates essentially nothing and reflects nothing. You would detect it only through its gravitational influence, which is, interestingly, exactly what researchers claiming to see the Planet 9 signal are doing. A fourth possibility is that the Hills cloud the innermost, densest part of the Oort cloud, thought to occupy the region between roughly 2,000 and 20,000 astronomical units, has enough mass and enough internal structure to produce the orbital clustering through its own gravitational influence on the extreme trans-Neptunian objects. This hypothesis eliminates the need for a single massive unseen body and replaces it with a distributed mass concentrated in the inner Oort cloud. The uncomfortable truth is that all of these models explain some subset of the observations and have trouble with others. None of them is a clean fit. The outer solar system's orbital architecture may be the product of a combination of influences, a distant planet, early dynamical chaos, galactic tidal effects, and observational selection effects, whose individual contributions are difficult to disentangle. What is not uncertain is that there is something to explain. The orbits of the extreme trans-Neptunian objects are not random. Something shaped them. We do not know what. And the answer, when it comes, will reveal something about the hidden structure of the solar system in every direction above and below the ecliptic plane. Part 19. The solar system isn't stationary. Everything you have experienced in your life has happened while the solar system was moving, not drifting slightly, not nudging gently, but racing the sun and all its planets and the Oort cloud and the heliosphere and you around the center of the Milky Way at approximately 220 kilometers per second. That is not 220 kilometers per hour, which would already be fast by any terrestrial measure. That is 220 kilometers per second. Every second that passes, the solar system moves 220 kilometers around the galactic center. By the time you finish reading this sentence, you have traveled more than 1,000 kilometers through the galaxy. The orbit around the galactic center takes approximately 230 million years to complete. In the 4.6 billion year history of the solar system, it has made roughly 20 complete circuits. The first multicellular animals had not yet appeared on Earth the last time the solar system was in the same position relative to the galactic center that it occupies now. The solar system is an old traveler, and the galaxy is a large road, and the route has taken it through environments that bear almost no resemblance to each other. Dense spiral arms, where star formation is active and supernovae are frequent, quiet interarm regions, where the interstellar medium is sparse and the heliosphere can expand freely, close approaches to giant molecular clouds that perturb the Oort cloud and send comets raining inward, perhaps even brief passages through the galactic disk's denser regions that expose the inner solar system to elevated radiation levels. This galactic orbit is the largest consistent motion of the solar system, and it connects the local story, the heliosphere, the cloud, the Oort cloud, to the galactic context. The structures above and below us are not just structures in space. They are structures that the solar system is moving through, encountering, and responding to on a continuous basis. The solar system is not a ship sitting at anchor. It is a ship in full sail, and the ocean it is sailing through is the interstellar medium of the Milky Way, which is structured and varied and shaped by the same stellar processes that created the local bubble and will eventually create the next bubble that the solar system passes through. Part 20. The hidden motion, vertical oscillation. The galactic orbit is the motion most people have heard of, if they have heard of any. But the solar system has another motion that is less discussed and in some ways more directly relevant to the structures immediately above and below the ecliptic plane. The Sun does not orbit the galactic center in a perfect circle in the galactic plane. It oscillates. It bobs up and down through the galactic disk like a buoy in water, crossing the plane of the galaxy, dipping above it, returning, crossing below it, dipping down, returning on a rhythm that has a period of approximately 60 to 70 million years per half oscillation. The mechanism is simple in principle. The galactic disk, the flat, dense region of the Milky Way, containing most of its stars, gas, and dust, has a gravitational center. The Sun, orbiting around the galactic center, is subject to the combined gravitational pull of all the material in the disk above and below it. When it is above the plane, the disk's gravity pulls it downward. When it crosses the plane and is below it, the gravity pulls it upward. The result is an oscillation, like a marble rolling back and forth in a bowl. The Sun is currently slightly above the galactic midplane by approximately 50 to 80 light-years, depending on the measurement reference used. It is moving upward further above the plane and will reach its maximum displacement in several million years before the disk's gravity pulls it back. In about 30 to 40 million years, it will cross the galactic midplane again and begin its descent below it. This oscillation matters for the structure above and below the solar system because the galactic plane is where the dense material of the Milky Way is concentrated. When the solar system is in or near the galactic plane, it passes through denser interstellar material, encounters more giant molecular clouds, and is subject to higher rates of perturbation in the Oort cloud. When it is above or below the plane, it is in relatively sparse, quiet interstellar space. The vertical oscillation subjects the solar system to periodic changes in its environment, periodic variations in cosmic ray intensity, in the rate of comet delivery from the Oort cloud, and in the density of the interstellar medium that the heliosphere is embedded in. The above and below of the vertical oscillation connects directly to the above and below of the ecliptic plane we have been discussing throughout. The galactic plane sits at a specific angle to the ecliptic, about 60 degrees, roughly, which means that the direction above the galactic plane is not the same as the direction above the ecliptic plane, but they are related. The galactic tide that acts on the Oort cloud and delivers comets to the inner solar system is tied to the solar system's position relative to the galactic plane. When the solar system is near the plane, the tide is stronger. When it is far above or below the plane, the tide weakens. The cometary delivery rate varies with the solar system's position in the galaxy, not randomly, but periodically, in a rhythm set by the vertical oscillation. Part 21. The biological question. Some researchers, looking at the geological record of mass extinctions on Earth, have noted a periodicity, a roughly regular spacing between extinction events of approximately 26 to 32 million years. The coincidence with the vertical oscillation period of the solar system has not gone unnoticed. If the vertical oscillation periodically puts the solar system in conditions that enhance comet delivery from the Oort cloud, and if cometary impacts contribute to mass extinctions as the Chicxulub impactor, a probable asteroid or comet that contributed to the end Cretaceous extinction 66 million years ago, suggests, is at least plausible, then there could be a connection between the solar system's galactic motion and the timing of biological catastrophes on Earth. This hypothesis is fascinating, and it is also contested enough that it deserves honest treatment. The claimed periodicity in extinctions is not universally accepted. Statistical analyses of the fossil record have reached different conclusions about whether the spacing between extinctions is meaningfully periodic or whether the pattern emerges from noise in a sparse dataset. The causal chain from vertical oscillation to increased comet flux to impacts to extinctions involves multiple steps, each with substantial uncertainty. And the specific period proposed, 26 to 32 million years, does not fit cleanly with the vertical oscillation period, which is estimated at 60 to 70 million years for a full oscillation, and 30 to 35 million years for a half oscillation, which is closer but still imprecise. What the hypothesis does correctly identify is a real physical mechanism, the periodic enhancement of comet delivery when the solar system passes through the denser regions of the galactic disk, and a real observational question about whether that mechanism leaves a detectable imprint on the biological history of Earth. The answer to that question is not known, but the question connects, in a precise and interesting way, to the vertical structure of the solar system's environment and to the galactic forces that act on the Oort cloud from above and below. Part 22. The largest invisible structure. We have been building outward heliosphere, cloud, bubble, Oort cloud, galactic orbit, vertical oscillation. Each layer is larger than the last, each governed by different physics, each connected to the layers inside it through detectable influences. But there is a layer that encompasses all of these, that extends to 300,000 light-years in every direction from the galactic center, that contains more mass than all the visible stars and gas in the galaxy combined, and that has never been directly detected. It has only been inferred from the motions of stars, from the bending of light, from the rotation curves of galaxies measured by radio telescopes in the middle of the 20th century. It is the dark matter halo of the Milky Way. The evidence for dark matter is not subtle. When you measure the rotation velocity of stars at different distances from the galactic center, the velocity profile you observe does not match the velocity profile you would predict from the mass of the visible material, the stars, the gas, the dust. If only the visible matter existed, stars far from the galactic center should orbit slowly, the way the outer planets of the solar system orbit slowly compared to the inner ones, because the gravitational pull from the central mass weakens with distance. Instead, the rotation velocity of stars in the outer galaxy remains roughly constant out to very large distances, far beyond where the visible material thins out. The only explanation that works within the framework of standard gravity is that there is an enormous amount of mass that does not emit, reflect, or absorb light distributed throughout the galaxy in a roughly spherical halo. The Milky Way's dark matter halo extends to roughly 300,000 light-years, 3 times the diameter of the visible disk. It contains, by current estimates, somewhere between 800 billion and 1 trillion solar masses of dark matter, compared to roughly 60 billion solar masses of visible stars and gas. Dark matter outweighs the visible content of the galaxy by a factor of roughly 10 to 15. The galaxy, we can see the 100 billion stars, the glowing nebulae, the bright spiral arms, is embedded in a halo of invisible matter roughly 10 times more massive than everything we can observe. The local density of dark matter in the vicinity of the solar system is estimated at approximately 0.3 to 0.4 solar masses per cubic parsec, or in particle terms, roughly 0.3 to 0.5 GeV per cubic centimeter, somewhere in the neighborhood of 1 dark matter particle per small volume, comparable to a coffee cup, depending on what each dark matter particle actually is and what its mass turns out to be. That local density means the dark matter halo is not just a distant structure, it is present here, now, around and through the solar system, through the Earth, through your body. Whatever dark matter is, it is moving through you at this moment, and has been for your entire life. Part 23. The intimate reveal. Dark matter passes through ordinary matter with almost no interaction. Whatever particles compose it, and their identity, is one of the deepest open questions in physics. They do not emit photons, they do not participate in the electromagnetic force, and they interact with ordinary matter through gravity and possibly through the weak nuclear force, but nothing else. This means they cannot be detected by any telescope that captures light. They cannot be felt by any instrument that responds to electromagnetic forces. They pass through walls, through the Earth, through your body, leaving no trace except the gravitational influence that reveals their presence in galactic dynamics. Except possibly occasionally, a category of dark matter candidates, called weakly interacting massive particles, or WIMPs, interact with ordinary matter through the weak nuclear force in addition to gravity. These interactions are rare. A given WIMP might pass through a light year of lead without a single interaction, but with a large enough detector, shielded from other sources of radiation, you might occasionally catch one. Several experiments have been built to try exactly this. Deep underground facilities filled with ultra-pure detector materials, looking for the faint recoil of an atomic nucleus struck by a dark matter particle. The most famous claim in this space is from the Dharma experiment in Italy, which has been running for decades and reports a clear annual modulation in its signal, a rise and fall in detection rate with a period of 1 year, peaking in June and reaching a minimum in December. The proposed explanation is the dark matter wind the solar system is moving through the dark matter halo, so there is a prevailing direction from which dark matter particles are arriving. As the Earth orbits the Sun, it sometimes moves into the dark matter wind and sometimes moves partially away from it, modulating the flux of dark matter particles hitting the detector. The annual cycle of the Earth's orbit should, if this interpretation is correct, produce exactly the kind of annual modulation in detection rate that Dharma sees. The problem is that Xenon, LZ, Panda X, and other experiments with different detector technologies have not confirmed the Dharma signal. They have placed limits on dark matter interactions that appear to rule out the WIMP parameters that would produce the Dharma signal. The conflict is unresolved. Either Dharma is seeing something real that the other experiments cannot detect due to their different materials or methods, or Dharma is seeing some systematic effect that mimics the dark matter signal, or the dark matter is something other than a conventional WIMP that interacts differently with different materials. The question is genuinely open. What is not open is the existence of the dark matter halo itself. The gravitational evidence for it is unambiguous. The dark matter halo is above and below the solar system in every sense of the phrase. It extends in every direction. It encompasses the heliosphere and the cloud and the bubble and the Oort cloud and the galactic orbit. It has been there since the Milky Way formed, and it will be there long after the Sun exhausts its fuel. It is the largest, heaviest, most encompassing layer of the structure we have been exploring, and it is, particle by particle, passing through everything you have ever known. Part 24. The final layer, structure beyond vision. Above the galactic plane, extending to tens of thousands of light years in both directions, there are structures that dwarf everything else in this story. The Fermi bubbles are two enormous lobes of high-energy gamma radiation extending roughly 25,000 light-years above and below the center of the Milky Way, discovered in 2010 by NASA's Fermi Gamma Ray Space Telescope. They were not predicted, they were not expected. They appeared in the data like two enormous beacons straddling the galactic equator, emitting gamma rays at energies that required an explanation involving either an enormous outflow of energetic particles from the galactic center or some past episode of extreme activity, possibly a burst of intense star formation, near the central black hole, or a period of accretion activity by the black hole itself that happened millions of years ago and is still visible in the form of this expanding, glowing structure. The Fermi bubbles are enormous, even on galactic scales. 25,000 light-years above and below the galactic center means they extend above and below the galactic disk by a distance roughly equal to the distance from the Sun to the galactic center. They are visible in multiple wavelengths, not just gamma rays, but X-ray, microwave, and even some radio emission. They are actively being studied, and their origin remains somewhat debated, though the leading models involve either a past period of activity by the Milky Way's central supermassive black hole, Sagittarius R star, or an extraordinary starburst event near the galactic center. The Fermi bubbles sit far above and below the solar system's current position in the galaxy. We are located roughly 26,000 light-years from the galactic center, and the bubbles extend to the same distance above and below the center, meaning they span a region that is far from our current location. But they are part of the same galactic structure that the solar system is embedded in, and their existence is a reminder that the galaxy is not a static, boring, evenly distributed pinwheel. It is a dynamic system with violent history and ongoing energetic processes, and the solar system orbits within it on a path that has, over 4.5 billion years, taken it through many different environments, some calmer than today and some almost certainly more dramatic. Beyond the galaxy, the cosmic web, the large-scale structure of filaments and voids and nodes that gives the universe its characteristic foam-like texture on scales of hundreds of millions of light-years, adds another layer of embedding. The Milky Way is part of the local group of galaxies. The local group is part of the Virgo supercluster. The Virgo supercluster is part of a structure called Laniakea, a supercluster complex that contains roughly 100,000 galaxies and extends for 500 million light-years. Everything we have discussed, the heliosphere, the cloud, the bubble, the Oort cloud, the dark matter halo, exists at a specific address within this structure, shaped by forces and histories that operate at scales so large that the human mind genuinely struggles to place them in any intuitive framework. The solar system is embedded in layers, and the layers do not end with the galaxy. Part 25. The pattern across all layers. Pull back and look at everything we have traced, not as a sequence of isolated structures, but as a single nested system, and a pattern begins to emerge. Disk to sphere, ordered to chaotic, visible to invisible, dense to diffuse, dominated by one force to dominated by another. This pattern repeats at every scale we have examined, from the transition between the planetary disk and the spherical Oort cloud to the transition between the structured heliosphere and the diffuse interstellar medium, to the transition between the visible stellar disk of the Milky Way and the invisible spherical dark matter halo surrounding it. The same geometric transformation, flat, ordered, rotational structure becoming three-dimensional, randomized, gravitationally dominated sphere, plays out at radically different scales. This is not coincidence. It reflects something fundamental about how rotating, self-gravitating systems work. The disk is the signature of angular momentum material that has organized itself along a preferred plane defined by its rotation. The sphere is the signature of either thermal equilibrium or long-term dynamical chaos material that has lost the memory of its preferred plane and distributed itself isotropically. The transition between the two tells you where the organizing force of rotation gives way to the randomizing forces of perturbation, collision, and gravitational chaos. In the solar system, the disk-to-sphere transition happens at thousands of astronomical units, where galactic perturbations overwhelm the angular momentum memory of the original nebula. In the galaxy, the disk-to-sphere transition happens at tens of thousands of light-years, where the dark matter halo, which never formed a disk because it does not dissipate energy through radiation the way ordinary matter does, surrounds the stellar disk in a roughly spherical distribution. The same physics, operating at scales differing by a factor of billions, produces the same geometric signature. This is one of the things that makes the structure above and below the solar system interesting beyond mere curiosity. It is a local example of physics that operates universally. Understanding why the Oort cloud is a sphere, what processes randomized it, how the galactic tide acts on it, gives you a window into the same processes that shape every other gravitating system in the universe. The solar system's layered structure is a laboratory for cosmological physics, accessible to our instruments in a way that distant galaxies are not, and the patterns it reveals repeat at every scale from here to the observable edge of the universe. Part 26. The boundary principle. Every boundary we have examined the heliopause, the edge of the local interstellar cloud, the wall of the local bubble, the outer edge of the Oort cloud, The boundary of the dark matter halo has the same fundamental character. None of them is sharp. None of them is a wall. All of them are gradient zones, where one regime of physics gradually gives way to another, where the balance of forces shifts continuously rather than discretely, where the identity of the medium changes through a process of transition rather than replacement. The heliopause is a pressure equilibrium that fluctuates with solar activity and with changes in the interstellar medium. The edge of the local cloud is a density gradient. The cloud does not stop abruptly, but thins gradually into the surrounding hot gas of the local bubble. The wall of the local bubble is a compressed shell, thickest where the supernova shock waves were strongest, thinner in other directions, and not truly closed. It opens into adjacent bubbles and cavities through gaps and channels in the surrounding interstellar medium. The Oort cloud does not have an outer edge so much as a fade-out. The density of objects decreases gradually from the inner cloud outward until you reach distances where the sun's gravitational dominance ends and the galaxy's gravity takes over. The dark matter halo has no known boundary at all. This consistent absence of sharp boundaries is physically significant. It reflects the nature of force fields, which do not suddenly switch off at a defined distance but diminish continuously with distance. It reflects the nature of fluids, gas and plasma, and diffuse particle populations, which do not have surfaces in the way solid objects do, but instead have gradients in density and temperature that can extend over large volume. And it means that the categories we use, heliosphere, cloud, bubble, Oort cloud, are human-imposed conceptual divisions on what is actually a continuous, graded physical reality. We draw the lines at the places where the dominant physics changes, but nature itself does not draw any lines at all. This boundary principle, every edge is a negotiation, not a wall, is arguably the deepest thing that the structure above and below the solar system teaches us about the universe. The solar system does not end. It shades. Its identity, as a coherent gravitational system dominated by one star, dissolves gradually into the identity of the galaxy that contains it through layers of transition that are as physically real as the planets themselves, but infinitely less visible to the kind of brief, surface-dwelling observers that we are. Part 27. The leak. The system leaks. Every layer of the structure we have traced leaks material and energy across its boundaries in both directions. The heliosphere is not a closed container. Cosmic rays flow inward through it. Solar wind particles escape outward through its downstream tail. Energetic neutral atoms cross the heliopause in both directions and carry information about both sides to any detector positioned in the inner system. The local cloud leaks interstellar neutral atoms into the heliosphere at a rate measurable by the IBEX mission. Those neutral atoms enter the heliosphere, interact with solar ultraviolet radiation, and produce a detectable glow that maps the properties of the cloud surrounding us. The local bubble leaks hot plasma outward through gaps in its compressed shell, mixing with the denser surrounding medium in a process that will eventually erase the distinction between bubble interior and exterior. The Oort cloud leaks comets. Every long-period comet that has ever been observed, every icy visitor that brightened the inner solar system with a tail of sublimated gas and dust was a leak from the invisible sphere. It was an object gravitationally nudged out of the cloud by a passing star or the galactic tide or some other perturbation, freed from its ancient orbit and sent on a one-way journey inward. These comets carry the chemistry of the early solar system, the organic molecules, the water ice, the pristine grains that have been preserved in deep freeze since before any planet existed, and they bring it into the inner solar system, occasionally delivering it to planetary surfaces, including Earth's. The Oort cloud leaks its history into the inner system in the form of these icy messengers. The dark matter halo leaks nothing that we can currently detect, because dark matter particles interact so weakly with ordinary matter that the concept of leakage is almost meaningless. But the gravitational influence of the dark matter halo passes through every boundary without difficulty, reaching the solar system as a component of the galactic tidal force, influencing the orbits of Oort cloud objects and therefore the rate of comet delivery to the inner system, affecting in principle, though perhaps unmeasurably, every gravitational calculation within the solar system. The solar system is not isolated. It has never been isolated. Material, energy, and gravitational influence cross every boundary in every direction continuously. The leakiness of the system is not a flaw in the physics. It is an expression of the fact that forces like gravity and electromagnetism have infinite range, that particle populations are distributed continuously rather than in discrete chunks, and that the universe does not respect the conceptual boundaries we draw on our maps of it. Part 28. The time dimension. The structure above and below the solar system is not only a structure in space, it is a structure in time, a physical record of history frozen into geometry. Every layer encodes a different epoch of the solar system's past, and reading those layers correctly tells us things about the solar system's history that no direct observation could recover. The Oort cloud is the oldest archive. Its objects were formed in the early solar system, in the disk of gas and dust that surrounded the young sun, and were then scattered outward by gravitational encounters with the forming giant planets, Jupiter and Saturn, flinging small bodies outward into the outer reaches of the system, where the galactic tide could circularize their orbits and trap them. The spherical distribution of the Oort cloud records the accumulated effect of billions of years of galactic tidal forces and stellar perturbations, every passing star that has come within a few light years of the Sun in the foul past 4.5 billion years has left a trace in the distribution of Oort cloud objects. Reading that distribution, if we could map it in enough detail, would be reading the history of the Sun's motion through the galaxy and its encounters with other stars. The local bubble is a younger archive. The supernovae that carved it occurred over the past 10 to 15 million years, and the expanding shell of compressed material at the bubble's edge records the cumulative effect of those explosions. The iron 60 in the ocean floor records one specific supernova event to an impact of stellar ejecta on Earth that can be dated with radiometric precision. The hot gas inside the bubble records the thermodynamic evolution of a supernova remnant over millions of years. The bubble is a physical record of recent galactic history, written in plasma and radiation and isotopes in the ocean crust. The dark matter halo is the oldest archive of all. It formed in the early universe before the first stars, as dark matter particles clumped together under their own gravity in the overdensities left by the Big Bang. The Milky Way's stellar disk formed later, inside the gravitational well of the pre-existing dark matter halo. The halo's current distribution reflects the history of the galaxy's formation and the mergers it has experienced over 13 billion years. Galaxies that were absorbed into the Milky Way long ago have left trails, streams in the dark matter distribution that are still detectable as perturbations in the galactic rotation curve. The dark matter halo above and below us is a fossil record of cosmic history stretching back almost to the Big Bang. Time is not separate from the structure of the solar system's environment. It is built into it. The layers we see now are the product of physical processes operating across timescales from billions of years to thousands of years. And understanding those layers requires thinking not just about what they are, but about what made them and when. Part 29. The unanswered core. After all of this, after the heliosphere and the cloud and the bubble and the Oort cloud and the galactic orbit and the dark matter halo, it is worth being honest about how much remains unknown. Not uncertain in the sense of slightly imprecise measurements, but genuinely, fundamentally unknown in the sense of not yet having a widely accepted answer. The shape of the heliosphere is not known. The IBEX ribbon remains unexplained. The IMAP mission, launched in 2025, is currently working to improve the map, but whether it will resolve the theoretical debate over the ribbon's origin is not guaranteed. Competing models of the heliosphere's shape, one resembling a comet tail with a long downstream extension, another resembling a more symmetric croissant shape with no extended tail, produce different predictions for the ribbon's behavior, and the data available so far does not cleanly favor either one. The first layer above and below us has an uncertain geometry. The mass of the Oort cloud is not known. We infer its existence from long-period comets, but the flux of long-period comets reaching the inner solar system is itself uncertain. Different models of comet delivery rates produce different estimates of the total Oort cloud population, ranging from hundreds of billions to trillions of objects. The total mass of the cloud could be anywhere from a fraction of an Earth mass to several Earth masses, with significant implications for the cloud's gravitational self-influence and for models of early solar system formation. Planet 9 has not been found. The orbital clustering of extreme trans-Neptunian objects remains unexplained by any universally accepted mechanism. The question of whether a large undiscovered planet, or a primordial black hole, or a captured rogue planet, or none of these exists in the distant outer solar system, is genuinely open and has been for nearly a decade without resolution. Dark matter has not been identified. The particles that compose it have not been detected by any laboratory instrument in a way that the scientific community is prepared to accept. Multiple experiments with different detector technologies have produced conflicting or negative results. The nature of dark matter is arguably the deepest open question in fundamental physics, and the fact that it permeates the space above and below us does not bring us any closer to knowing what it is. These are not small gaps to be filled by the next generation of instruments in a decade or two. They are fundamental uncertainties that reflect the genuine limits of current knowledge. The structure above and below the solar system is real, layered, physical, and largely inaccessible to direct observation. We are mapping it with secondary signals, with the shadows it casts on things we can see, with the fossils it leaves in ocean sediments, and the trajectories it inscribes on distant comets. The map is impressive. It is also profoundly incomplete. Part 30. Closing frame. Let's reassemble everything, one last time, from the inside out. You are here, on the surface of a rocky planet orbiting a middle-aged star. The star is continuously exhaling a bubble of charged particles that extends in every direction above, below, sideways, at every angle to roughly 100 astronomical units. Inside that bubble, the planet's orbit, the asteroid's drift, the Kuiper Belt objects circle slowly beyond Neptune, and two ancient spacecraft travel outward with instruments that were built by people who are now dead. The bubble is asymmetric and imperfectly understood. It leaks. Its boundary is currently being mapped by a spacecraft launched last year. The bubble is embedded in a cloud of warm, partially ionized hydrogen and helium gas roughly 30 light-years across that the solar system entered 60,000 years ago. The cloud is drifting, the solar system is drifting through it, and the exit is approximately 2,000 years away. When the solar system leaves the cloud, the heliosphere will respond to a new interstellar environment. The cloud is not the vacuum that the flat plate image implied. It is a structured, magnetized medium with temperature and density and composition, and the solar system is moving through it at 26 kilometers per second. The cloud sits inside a cavity roughly 1,000 light-years across a bubble of hot, sparse plasma carved out by the explosions of between 14 and 20 massive stars over the past 10 to 15 million years. The iron from those explosions is in the floor of the Pacific Ocean. The cavity is the immediate galactic neighborhood of the solar system, and the solar system's current position within it, near its center, may reflect the history of stellar cluster membership that shaped the early solar system. Surrounding all of this, beginning roughly 2,000 astronomical units from the Sun and extending to 1 to 2 light-years in every direction, is the Oort cloud, a spherical shell of trillions of icy bodies, never directly imaged, inferred from the trajectories of long-period comets, being continuously perturbed by passing stars and the gravitational tide of the galaxy. Its outer boundary marks the edge of the Sun's gravitational dominance, the point where the galaxy's gravity begins to compete with the Sun's, the true extent of the solar system as a gravitationally coherent entity. Something may be perturbing the orbits of objects in the outer solar system in ways we cannot fully explain. We are looking for it. We have not found it. The solar system is in motion, orbiting the galactic center at 220 kilometers per second, completing one circuit every 230 million years, oscillating above and below the galactic plane on a period of 60 to 70 million years. As it moves, it passes through different regions of the interstellar medium, different densities, different temperatures, different magnetic field geometries, and the heliosphere responds to each transition. The solar system has been doing this for 4.5 billion years, traveling through 40 different galactic environments since it formed, each one shaping its outer layers in ways that are recorded in the Oort cloud's distribution and the local bubble's geometry. And through all of it, through the heliosphere, through the cloud, through the bubble, through the Oort cloud, through the galactic disk, in every direction, above and below the ecliptic plane, and perpendicular to it, and at every other angle, the dark matter halo of the Milky Way extends to 300,000 light-years, pressing its invisible gravity on everything, passing through everything, containing by mass more than 10 times everything visible in the galaxy, and remaining, despite decades of direct detection experiments, as mysterious as it was when the first rotation curves were measured in the 1960s. This is the solar system, not the flat plate, not the tidy image with the Sun in the center and the planets on a line and a vague edge past Pluto. A layered, spherical, dynamic, leaking, moving, nested structure embedded in layers of other structures that extend from 100 astronomical units to 300,000 light-years, from things we know well to things we cannot see, from processes we understand to phenomena we cannot yet explain. The textbook image was a cross-section of the middle. All of this is the whole thing, and the most honest thing that can be said about it is the thing that the evidence demands at every layer, from the heliosphere, whose shape we cannot fully determine, to the dark matter whose nature we do not know, to the Oort cloud we have never directly seen. The solar system above and below you in every direction, through scales you cannot visualize and time scales you cannot feel, is full of structure we cannot yet see. That is not an admission of failure, it is an invitation. Every unanswered question in this story, the ibex ribbon, the orbital clustering of the trans-Neptunian objects, the nature of dark matter, the geometry of the heliosphere, is a specific, measurable, addressable problem that instruments currently being built, or already in flight, or being designed in research labs right now, may answer within the next generation of human lifetimes. The structure above and below the solar system has been invisible to us for almost all of human history. We have been systematically discovering its layers for less than a century. The rate of discovery is accelerating. And the discovery, when it comes of the object shaping the outer solar system's orbits, of the particle composing the dark matter halo, of the detailed shape of the heliosphere, will not make the solar system simpler. It will reveal new layers beneath the ones we thought were the deepest. The universe has a long history of doing exactly that. Every time we thought we had reached the last layer, there was another one below it. Every time we thought we understood the boundary turned out to be a gradient with something interesting on the other side. Every time we looked at what we thought was empty space above and below us, we found that it was full of structure, full of history, full of physics, operating on scales that dwarf anything the human mind was evolved to handle. There is no reason to think this pattern has ended. There is every reason to think the next layer is already there, waiting in every direction above and below you, right now, in the form of evidence we are not yet interpreting correctly, or instruments we have not yet built, or mathematics we have not yet written. You live at a specific address, third planet from a middle-aged star, in a warm cloud inside a supernova-carved cavity, at the edge of a galactic disk wrapped in an invisible halo, moving at 220 kilometers per second through a universe that has been building structure since the first fractions of a second after the Big Bang. That address has more layers to it than any map has ever shown, and the layers above and below you, in every direction you cannot see from the surface of a small blue world, are full of structure we cannot yet see.